Next up, we have Dimitris Vianopoulos, who is Technology Development Specialist at Cargill. He focuses on organic polymer additives, and he's going to tell us about the company's latest developments in this field right now. So over to you, Dimitris.
Thank you very much for the introduction. Hello, everyone. My name is Dimitris Vianopoulos. I work as a technology development specialist for Cargill, for the polymer additives business of Cargill. Trying to find out how do we change slides. Probably this one. Cargill is a very big company, US-based. It's mostly known for the natural products, agricultural products that it produces, from protein, soy, oil, many different things that are produced by nature and they are edible. That's the vast majority of Cargill's business. However, over the last 6 years, there is a new group called Cargill Bioindustrial, and in that group, we take products that are ingredients that are naturally produced, but they're not edible, so they can find industrial applications. So the bioindustrial group has different businesses. One of them is the polymer additives business, where we have organic additives for all sorts of thermoplastics. So this is just an overview of only the bioindustrial group of Cargill, which, as I said, is the smallest part of the overall company. You can see different sites all over the world. The main sites for the polymer additives business are in York, Hull in England, Tampere in Finland, Gouda in the Netherlands, Shanghai in China, and then lots of other places, as you can see. A company of the size of Cargill, which is very big, it has 160 years of history and over 160,000 employees, has, of course, very important sustainability aims, because if these aims are achieved, then the impact can be huge. So we have clear targets for climate, land, and water, and people. But obviously, today I'm going to talk about the part of polymer additives and the effect that we can bring into the circular plastics economy. Speaking of which, and mentioning and showing these statistics here, you can see that things aren't really great. There is a decline in the overall sustainability, unfortunately. However, this gives the potential for a lot of improvement, definitely with regards to how much plastic ends up in oceans, so there's only room for improvement, hopefully, as well as the reduction of greenhouse gas emissions. And of course, with that and all the effort and activities that will take, the amount of money that can be generated, as well as the jobs that can be created. From our business, the polymer additives business, we have great examples for all 4 R's of the circular economy, which is reduce, reuse, recycle, and redesign. Lots of examples in the first 2. For example, with our additives, we can downgauge significantly the thickness of films and therefore save some material. A very good example in reuse, which links to Leonardo's presentation. So we have excellent anti-scratch additives, which can prolong the longevity of plastics in car interior, because they protect it from scratches. But lately, over the past 5-6 years, we've been investigating a lot the effect of our additives on recycling and redesign. And there's a very nice study to show you today. This is an overview of our products in polymer additives. Most of them are around friction control, so the quite well-known slip additives, anti-block additives, mold release, anti-scratch, torque release, and additives for easier processing of higher value plastics, so non-polyolefins, as well as very good anti-static additives, short-term, long-term, and some specialties like bio-based plasticizers and anti-fog additives. The focus of this presentation is on Incroslip product range. This is the higher quality range of amides that we have, which not only give excellent performance, but they also have excellent organoleptic properties for food applications, for more sensitive applications. So they perform much better than the common erusamide and similar additives. So we started by investigating the effect of the additive on a product, and ideally a product that can be easily recycled, and in the UK, for example, is one of the prime examples of closed-loop mechanical recycling, using and reusing the milk bottles. So we did a series of tests using an extrusion blow molding equipment and an ABA bottle structure where the middle layer is recycled HDPE and the inner and outer layer virgin HDPE. And we added in the inner and outer layer the additive, our additive, which is Incroslip C, via master batch. Straight away, we reduced the temperature significantly because this should be the aim for all converters, to save energy and to protect the polymer from degradation. We found out straight away that with the use of the additive, we would use different speed profiles, we could widen the processing range, and that is a positive thing. More importantly, we could see a reduction of the cycle time. So for the same conditions, without the additive, we needed 100 seconds to make the bottle. With the additive, that was reduced to 85 seconds, a nice and clear 15% reduction. This is quite common in general with the use of with the right use of our additives, that you can improve the output rate. And this is something nicely demonstrated in the EBM bottles. We also pushed the material quite a lot, trying to add more and more recycled HDPE and minimize the amount of virgin HDPE. This was achieved in every combination when the additive was used. However, in the same conditions, blank material was failing to produce the bottles. It was either the extruder was either stopping, not working at all, or after a couple of seconds, you could see that it was reaching its limits. And also the save energy and less degradation to the polymer that can be achieved by using the additive and enabling the reduction of the processing temperature, in this case by an impressive 20 degrees Celsius. So these results were nice and clear. And here is the summary with all the highlights of this study. So we can expand the processing window when we use the additive. We can use different conditions, especially extrusion speeds. We can save energy in the material, during processing by reducing the temperature 20 degrees or similar, and of course protect the polymer from degradation. We can increase the output rate, so we can make things faster. We have similar examples in film extrusion and other examples. And of course, we managed to increase the amount of recycled plastic in this formulation and even go up to 100% at very challenging conditions where blank material could not cope. So then the idea was, once we make these bottles, or once we have our product, whatever that may be, in HDPE, then you want to recycle it and you want to find out what is the effect of the additive in the recycled plastic. And we've done that not only with HDPE, but also with PET and polypropylene. So we have very similar studies in all three polymers. If you're interested in more data, please contact us. We collaborated with Aimplus, where we sent all the materials so they can perform the study. We did two studies, one simulating post-industrial waste and one post-consumer waste. Of course, initially starting from a very clean virgin material. We used the Recyclass protocols for the hot bottles of the very challenging conditions in terms of washing with caustic soda, 90 degrees temperature, etc. We produced specimens, shredded them, washed them, repelletized them, and repeated that for 3 times. We found that there is an effect of washing on the concentration of the additive. So we started with a high concentration of around 0.5%. Then we saw that within 3 cycles it goes down to 0.25, so half of it was lost, but still the remaining amount is enough to give very good effects. And again, this is a summary of the study. So As expected, we didn't see any impact on the mechanical properties. We know full well that these additives at these amounts are not plasticizers, so the mechanical properties remain the same. The color, as you can see, it's better with Incroslip-C, not because the additive makes it whiter, but because the additive protects it from degradation, which is important. And we saw an increase in the MFR, in the melt flow rate. So after the end of the third cycle, there was a reduction in the MFR of HDPE, which is expected, typically due to cross-linking. With the additive, it was increased by 2 times, which was a great thing to see. This is exactly what I'm talking about. You can see the blue column, which is reduced down to 0.5 from around 2.2. That's on the blank recycled HDPE. With the additive, it's on just over 1, so it's 2 times better. That was enough for us to start getting more and more curious and trying to understand what is happening, why is this taking place, and what is the mechanism. So we moved on to capillary rheology to investigate it a bit further and more in depth. And we repeated all these 3 cycles again. What we found, if you focus on the right-hand side, the red line is blank, is virgin HDPE at the first conversion cycle. After 3 recycling loops, the viscosity, shear viscosity goes up, which means the polymer is degraded, is getting degraded, and there is cross-linking, which restricts the flow. With the additive, you can see that after 3 cycles, there is barely any change, which means the additive allows HDPE to retain the original properties much better. So in summary, yes, we can say that the amides, they act as internal lubricants, so it has nothing to do with the mechanism of antioxidants. The antioxidants are needed, and they help the polymer through a very specific function, of course, chemically interacting, but the amides are also protecting through a mechanical way with internal lubrication, easier flow, and reduction of the degradation. And obviously, since we use the commercially available grade, that means that there were antioxidants in the polymer, and therefore the combination of antioxidants and our additive had a very nice synergy. Yes, so the conclusion, of course, is that with the right use of amides, if you learn how to use them properly, you can protect your polymer from degradation, and you can improve processing significantly. And of course, yes, we are very happy to collaborate with whoever is interested in exploring this kind of phenomenon further and further, and see if we can achieve proper recycling solutions. Thank you very much for your attention.